In this video, we're going to look at oxygen. Let's start here with the plant. In the plant, this P is equal to 0 or diamagnetic form. The traditional double bond is formed, and then it takes and moves away, and it releases 94 kilojoules per mole, and it goes to this ground state form where it is a 90-degree rotation. Now there's two unpaired electrons, P is equal to 2, and this is the what I use is the electron dot structure. It's a simple rotation. Now what I have here is a model showing this. This is the form here where I have the two unpaired electrons. This is the ground state. If I take and do a simple rotation, we'll take and go to the form on the right where you had the traditional double bond. You notice the sp2 electrons, these are eclipsed, and so that would count for the increased energy. Now, here I have add an electron, and you're going to get the superoxide. So let's take and look at what might happen here. Let's take and add an electron to this position here. Let's say we do this. And now what would happen would be, you've got an electron pair, and this is going to take and release the system. Going to take in, let me see here. And you're going to get this form where you have a p orbital, and you got the two electrons in the p. Now this could hybridize to sp3 because this is a negative. You've got 2, 4, 6, and 1 is 7, negative 1. Since this is a negative, it's no longer pulling on this p orbital electron, and so what I'm going to show is that this is going to take and push away. And so now, like I say, if this is showing a bond order of 1, and I've seen where the bond order for superoxide is 1.5. This one is a p orbital electron. That would be high energy, and it could be pulling these the p orbital electrons in this direction. So that's what would happen for the superoxide. Now, the lungs in the atmosphere has this form. You breathe it in. The iron plus 2 of the heme is going to find this O2 where it's paramagnetic, and you're going to bind to the iron plus 2, and this is going to be the form that you're going to have. Now, I think what happens is that it bonds in this form originally. But what happens is this energy from the system, the oxygen bonding to the iron plus 2, is sufficient for the 94 kilojoules per mole, and this is going to take and rotate to this form. certainly in this form is going to be transferred. Hemoglobin is a simple transformation or transforming or transporting of the oxygen to the cell. Now in the cell, you have the oxygen, and it's going to take and add 4 electrons and 4 protons, and you go into 2H2O. So there's some controversy about what is going on with that process, and we're going to go through it. What is the information? Well, myoglobin is paramagnetic. Hemoglobin is paramagnetic. Going back, the heme is paramagnetic. But when you take and add oxygen to the hemoglobin, it is, or myoglobin, either one, but hemoglobin subunit, it is now diamagnetic. So how do you account for the diamagnetism of this? Well, I think we already saw the oxygen. The oxygen, once it's going to bind, the energy is sufficient for the rotation, 90-degree rotation, and that would be the diamagnetic form. Some very wonderful information. The infrared data. The bond order is around 1.6, not 1, not 2. It's around 1.6. So how do you account for that? The X-ray photoelectron data, the iron ion is approximately 3.2, not plus 2. But we know that the iron plus 3 does not transport oxygen. It binds to two heme units in the plus 3 state. Some of the suggestions for this data is low spin Fe plus 2 binds to singlet O2, which again, I don't think that happens. I think it binds to the triplet, and then it isomerizes. The low spin Fe plus 3 binds to the O minus 2, and then this is the form that is shown where you take and have a superoxide form. I certainly do not think superoxide is involved, and we'll see later why that may be, why it may not be. Okay, let's take and look at what we have done here. The iron, we're looking at the paramagnetism in the heme, and then you go down to the oxygenated hemoglobin, and it becomes diamagnetic. Now, the iron plus 2 has electronic configuration of 4s0, 3d6, 4p0. I'm going to take and use hybridization because these four nitrogens are identical, and they're planar due to the ring, and then as you add another nitrogen in the 5th position from the hemoglobin subunit or the myoglobin, that would be a different one, and then you have the oxygen added. So it is not symmetrically, spherically symmetrical, and so I think that's probably the best explanation would be that it hybridizes. Now, this would be hybridized, I'm showing sp3d2, and then there would be 3D orbitals left over. Okay, so now let's suppose that this protoporphyrin 9 binds to the Fe plus 2. There are going to be two protons released. This is the heme structure, and I did not find the paramagnetism or heme, but anyhow, there are two possibilities that you can have. These would be the four nitrogens, 2, 4, 6, 8 electrons. You've got two electrons here in 5th position, 2 in 6th position, and then that would give you electron and electron in the 2 of the 3 Ds. Or for P is equal to 4, you could have the same 4 here. You have 1 electron here, 1 electron here, 2 electrons, 1, 1. So either way, the heme is going to be paramagnetic with 2 unpaired electrons, or it's going to be paramagnetic with 4. I probably would suggest this form. But anyhow, that's the heme. That's it. Not here nor there. What we do know is that the myoglobin and the hemoglobin subunit, and we have a histidine nitrogen added at the 5th position, and we know that it is paramagnetic. So again, you're going to have these 4. You're going to have the nitrogen pair, and then you'd have the pair left over, and you'd get 2 electrons here and 1, 1. So this would be a paramagnetic with 2 unpaired electrons. If we take and had the odd electrons in here, you get this one, you'd have 1 electron in the 6th position, and you get 2, 2, and 1. So either case, the hemoglobin subunit or the myoglobin is going to have 2 unpaired electrons. What happens to the oxygenated myoglobin or the hemoglobin subunit? This position 6, the oxygen comes in, it has to bond through an sp2 pair of electrons because the bond angle is well known, 121 degrees. So now this oxygen pair of electrons is going to come in, and you're going to take and move either one or the 2 over to the right. Now this would be over here in the 3D, 3 orbitals. You have 2 electrons, 2 electrons, 2 electrons. So what you have here is you have 6 and 12 electrons. 6 is 18, and you're going to have a complete shell. As I said before, this would account for the diamagnetism in the oxygenated hemoglobin subunit or the myoglobin. Initially, like I said before, I think what happens is that the on binding the oxygen, there's a sufficient amount of energy, but it bonds in the triplet form. Enough energy to cause the isomerization, the simple rotation, and you go to the double bond form. So that would count for the heme subunit of the heme subunit or the myoglobin. Let's take and look at the bond order of 1.6. What I'm suggesting is once this oxygen bonds, it's going to bond in the lungs. It's going to bond at atmospheric oxygen, if you will, which means that there's 2 unpaired electrons. And now there's a 90 degree, and it's got to have 94 kilojoules of energy. And again, what happens, I think, is just think about it. The oxygen binding to the heme and the heat going to be produced if it's not isomerizing. But since it's going to isomerize and picks up 94 kilojoules per mole of energy, that energy is stored. And it does two things. It keeps the lungs cool, I would think, and also it's going to be the high energy form when it gets to the myoglobin and is transferred over. But anyhow, it's going to rotate, I'm proposing. Simple double bond here. You've got a pair of electrons, so this oxygen, the formal charge is 0. Over here you got 2, 3, 4, 5, if you will. Or it depends on how this bond is here. If the oxygen belongs to the oxygen. But anyhow, we're talking about it's taking on some positive character to be +1. So now we have T is equal to 0. Diamagnetic oxygen. The iron has no orbitals to form a traditional double bond, but anyhow, there's an iron dipole, and this pair of electrons could move into here, and now you're going to get a double bond, and we'll see this when we get into the transfer of the oxygen to cytochrome C. So now we have here a double bond and you have a single bond. So the double bond and the single bond is going to average out to about 1.6. Two bond order of 2, bond order of 1. So it'd be 1.6. How about the charge of 3.2? Well, the 3 d orbitals each has a pair of electrons, and this pocket is going to be positive. Now here, +1, and you're taking away some charge from the iron, but there's a pocket. You got positive, positive, positive. There's a pocket here, and one of the pair of electrons in one of the d orbitals possibly could move down into this region. This happens all the time, especially in biological systems, and that would account for the apparent oxidation state of 3.2. But that doesn't mean that the iron has oxidized to +3. It is an apparent temporary state of 3.2. Now let's take and look. Let's take and look at what happens when the oxygen gets to the cell and it's attached to the myoglobin. Let's look what happens to prevent the production of superoxide. This is cytochrome oxidase will catalyze the transfer of 4 electrons from cytochrome C to oxygen. Now, I'm not going through this in ultimate detail. You can look at it and see that I've got whether I have the electron flow correct or not. Now, this is from Stryer, and the references in Stryer. But anyhow, we'll start out here with iron +3, copper +2. This is a system that, again, if the iron is in 3 state, there would be 2 heme portions which would trap the oxygen in between. But this one has got iron plus 3, copper plus 2. It adds 2 electrons. The first electron goes to the copper plus 2, reducing it to plus 1. The second electron goes to the iron plus 3, reducing it to iron plus 2. Now, the oxygen, which is in the diamagnetic form, singlet state, can take and bind to the iron. And so what I'm suggesting is that this iron gives up an electron to this oxygen. The pi system, 1 electron goes here, 1 electron goes here, and the copper gives up an electron to that one. And what does that form? Well, you got iron plus 3. I'm showing the coordinate covalent here now. It's plus 3, but this pair of electrons belongs to the oxygen. We've got two electrons, signal bond, negative, negative. We got a negative, negative, and we got Cu plus 2. Now what happens now is 2 protons and electron adds, and I'm just showing here stepwise what I think is going on. The 2 protons is going to add to the oxygen. That's going to make that plus. You still have the minus here. Then what happens is the iron plus 3 can actually lose another electron, gives it up to, and I've put it in here in this area, and the external electron comes in for here, and that would kick out the water, and the water is going to bind to the Cu plus 2, the copper plus 2, and that's going to leave iron plus 4, oxygen minus 2, and these 2 electrons are on the oxygen. Now we have two protons going to add, and we have an electron to come, and you go right back to the cycle. So that's what happens to stay away from the high energy superoxide in the cells.